So what's a measure? We tend to think of it probabilistically, saying mu for measure. If you have some volume in d dimensions, denoted dx, I'll be dropping these here, but then we tend to say the likelihood that we are in this volume is some density function rho x. The way we can define measure in dynamics is that when we look at our state space, we can partition it in the regions, and we can associate to every region its own little measures. So we can say, I'm performing an experiment, physical or numerical, and in the region, I can project it by defining a characteristic function. The state space that takes a value 1 if x is in the region, mu1, and 0 otherwise. And then I can define the mass or the number of state space points that I'm tracking in that volume. So I can define d mu1 to be an integral over measure times this characteristic function over the whole state space, but this projects only what's here. And I can think of this as just as the measure over this volume. Or if you find this mu confusing, you can always write it the way you're used to. Some density functions times dx over subvolume mi. So this is a key concept of statistical mechanics. It's called coarse graining. Well, mathematically, we can talk about a particular point x in state space to infinite precision. In practice, we talk about it only to finite precision, and that's defined by some volume in which this point is picked. Every other point in the same volume is the same up to that precision. And this is the bridge between determinism and statistical mechanics. The fact that even if we assume that our laws of motion are perfect, and we know evolution on any state space point to infinite precision, the moment that we say that we can categorize states to finite precision in coarse grain, we have produced a probabilistic element because it's someplace in there. So now it'll be a little bit confusing again because everything we'll derive this week is exact, deterministic. It's an exact Schrödinger equation. There's nothing to discuss. It's just equation that describes evolution of densities, or in case of Schrödinger equation, amplitudes. So there's no probability. And we'll take a limit of coarse graining goes to infinity. So we really talk about these functions rho x. But it's at this level that we start realizing that going forward in time and backward in time is different. That we cannot, even though individual trajectory can be computed equally well backward and forward, the evolution in the direction of time is different than reversible. And I will not cover in this course, but there is a great deal of progress in foundation of statistical mechanics along these lines in the last 2 decades. When people can explicitly compute violations of various fundamental statistical laws like increase of entropy, decrease of entropy. We will not take this path very much. I mean, we'll discuss diffusion, but not go into foundational issues. So this is where it happens. And now it's convenient. When you do your experiments, you might just take your state space and sprinkle it with 7,307 initial conditions. So the mass will be so many grams or kilos. But that's obviously not the important thing. The important thing is just the normalized density. So you want to normalize this density. So when you sum up your whole state space and all the coarse grain volumes, you want this to sum up to 1. And that you can do in any numerical experiment in this description. So then you can really think of this as a probability. It's just a probability that your condition is in some finite region, whereas the evolution will remain exact, deterministic, not stochastic, no external noise, nothing. So you can think of your rho delta x to be a limit of delta mu I goes to 0. So finer partitioning, as long as the point you're interested is still within that infinitesimal volume of this kind of coarse grain measured. And in that limit, the normalization is known as probability conservation, or that says that density integrated over the whole state space is 1. And for now, we'll imagine the state space is finite, so we don't worry about volumes, etc. It's not essential. You can do it for infinite state spaces as long as they're normalizable.